All right, so when we're looking at measuring the size of earthquakes, we can measure them in terms of two different ways. One is intensity and one is magnitude. Now, magnitude is the one that we talk about the most. And so anytime there's an earthquake that takes place anywhere in the world now, everybody questions how big it is in terms of magnitude on the Richter scale. So magnitude is simply the amount of energy that gets released from the focus. So it's all about the amount of energy. Intensity is a measure of the degree of shaking at a given location based on the amount of damage perceived. And I just want to point out that the amount of damage perceived is in the eye of the beholder. So somebody has to look around, make observations, come up with how much damage is done, and then say, okay, here's how intense this earthquake is. This one is purely mathematics based on a certain amount of energy that actually gets released. So I just wanted to specify that. So maybe this one is more old school and this one here is more modern. So the two scales that are used for measuring the size of earthquakes are the Richter scale and the modified Mercalli. It's pretty safe to say that the modified Mercalli is pretty old and that the Richter scale is the more newer one that we use. So the modified Mercalli uses intensity, so it's based on the amount of destruction, which is based on human observations, which is totally problematic. Because it's so old, it uses Roman numerals, and they've closed it off. So it starts with Roman numeral 1 and ends with Roman numeral 12. And so if you did get an earthquake that was, way bigger than anything we ever thought possible, then the scale's closed, and it doesn't account for anything bigger than a Roman numeral 12. The Richter scale is based on magnitude, which is the amount of energy released. It is decided upon using special instruments called seismographs. It uses regular numbers that we use every single day, and the scale is left open just in case we someday get an earthquake that's way bigger than we've had in the historical past. So here we look at the earthquakes in terms of magnitude, and just a couple of things like an energy bolt and from a lightning bolt, would be equivalent to a magnitude of 2. So we think of like a bolt of lightning to be so powerful, but yet it's only a 2 on the Richter scale. 1,000 pounds of explosives would basically be a 4 on the Richter scale. If you were to look at the 1906 San Francisco earthquake, which I spoke about in a previous video, it was an 8 on the Richter scale. And so just to give you some idea, in 1946 they let off an atomic bomb called the Bikini atomic bomb, and that would have registered a magnitude of 6 on the Richter scale. So I'm just trying to give you some ideas about magnitude and how that equates in terms of energy in other scenarios. So here's the modified Mercalli scale. As you can see, if it's a Roman numeral 1, you don't feel it. Roman numeral 2, felt only by persons who are lying down or at rest. Roman numerals 3 to 4, felt by persons indoors only. 5 to 6, felt by everybody. Some damage to plaster and chimneys. A lot of people don't even have chimneys anymore, so there's an issue with this scale. Roman numeral 7, people start to run outdoors, damage to poorly built structures. 8, well-built structures slightly damaged, poor-built structures suffer major damage. I mean, how do you qualify if something's poorly built or well-built? Then buildings shift off foundations. Some well-built structures are destroyed. Few masonry structures remain standing, etc., etc. I mean, the last one is total damage, and you actually see waves on the ground. So there's a lot of problems with this scale. I mean, it's basically so that when humans are actually watching an earthquake take place, what of these things do they see so they can assign a Roman numeral? And this is more of an older scale. So with the Richter scale was introduced by Charles Richter, and as we say, it's based on magnitude. And there's a couple numbers here that's really important. So for example, it's important that everybody know that when you go up in magnitude just by one number, there's 30 times more energy released. So for example, if you had a magnitude of 4 or a magnitude of 5, the magnitude of 5 would have 30 times more energy released because there's one number between a 5 and a 4. Between a 4 and a 6, there's 2 numbers in between. So to go from the 4 to the 5, there's 30 times more energy. To go from the 5 to the 6, there's 30 times more energy. that would be 900 times more energy between a 4 and a 6, because you'd have to go 30 times 30, which is 900 times. This only applies to energy and magnitude. If we're talking about the amplitude on an S wave, then we are not talking about the 30 times, we're talking about 10 times. So for example, an earthquake of 6 got 10 times more amplitude on its S wave than an earthquake that's a magnitude 5. 10 times 10 is 100, so a 7 would have 100 times more amplitude on its S wave than an earthquake of 5. In order to locate an earthquake, you're going to need an earthquake's epicenter. You're going to need 3 stations. So a lot of people think of this in terms of triangulation. So you're going to need 3 seismograph stations, and you're going to need 3 different seismograms. On a particular seismogram, you can calculate the amount of time in between the arrival of the first P and the arrival of the first S, which is typically in minutes. So for example, imagine if you determined that there was 6 minutes between the arrival of the P and the arrival of the S at a certain station. You can take that time difference, go to a travel time graph, and you can plot that time difference and see where it basically falls on the graph, and then you can figure out your exact distance from that earthquake's epicenter. And you could draw a circle around your station that distance away. And you would have a circle all the way around your seismograph station. Of course, one circle is not enough because the earthquake could be anywhere on that circle, so you'd have to bring in the second circle, the second station, and then 2 circles would intersect each other at 2 points, still not enough. Then you would have to bring in the third station with the third seismogram and a third circle, and then the third circle would go through one of those 2 points, and that would be where the epicenter is located. So, just to explain, if you were to look at this seismogram, as you can see right here, this is just background noise, we don't care about this. This is when the P arrives, this is when the S arrives. So this distance from there to there is what we could talk about, the PS time interval. So you would need to know the amount of time in between that P and S wave, and then you would go to your travel time graph and you would be able to figure out how far away from your station that earthquake is, so you could draw the appropriate circle around your station on a map. And then you'd have to call a friend at another station and another friend at the third station, 3 circles, and they would intersect at 1 point. So here is a travel time graph, so it's important that you see this. And so for the particular diagram we just looked at, we measured the P and S time difference of the arrivals, and they seem to fit between this. So here's your P curve, and here's your S curve, and they seem to fit right here. So this is where they fit. That time difference fits between here. Then you come straight down and you realize that your 9,500 kilometers away from the earthquake. And so now you can draw a circle around your station with a radius of 9,500 kilometers. So as you can see in this particular location, New York City got a really big circle, meaning that, so here's New York City, meaning that the earthquake is a really long ways away. And then we have B, which is Berkeley, which is in California. And we have the blue circle. And then the third place we have is Denver, Colorado. And we have the third circle, And then all 3 circles intersect at this 1 point right here. And so that is the epicenter of the earthquake. Go directly below it, and you will get the epicenter. Here's some damage caused by an earthquake that occurred in Alaska in 1964. Here is some more damage that occurred in San Francisco from the 1989 earthquake. And one of the things that you can't really see in this particular diagram, but a lot of times if you have like a quicksand or a liquefied sand, when the ground actually shakes so much, the ground actually settles, and any water that's in the ground is forced to come up through it. And basically it just becomes really, really liquefied, and a lot of times buildings collapse or they sink down into the ground because of this process called liquefaction. So some of the things that we have to worry about with earthquakes is basically sometimes earthquakes trigger tidal waves called tsunamis, and some people call them seismic sea waves. Sometimes if the ground is very, very unstable and an earthquake comes through, it can create a landslide, Sometimes it can cause the ground to collapse, or what's called ground subsidence. A lot of times if there's gas lines or electrical lines or anything of that nature, fire can also be another result of earthquake. There's no real way of predicting if an earthquake is going to come. I mean, like, you know that if you are on a plate boundary or near a stationary hotspot, then the possibility exists for earthquakes and volcanoes as well, except for a transform plate boundary. But anywhere on a plate boundary or a hotspot, you know it's a bad place to be for earthquakes, so you can pretty much predict that they're actually going to happen. In terms of the short range, yeah, there's people out there trying to get an idea of when the next earthquake is going to take place in a certain area, but there's really no reliable method for that to actually do it. Long range predictions gives the probability of a certain magnitude earthquake occurring on a time scale of 30 to 100 years. But I mean, 30 to 100 years is within, the human life expectancy. So really, there's really no predictions that you can do to know that an earthquake is going to come. You can just avoid plate boundaries or take a risk.